You know that feeling, right? You're staring at a blinking network light on a switch, and you just know that one single cable is the only thing holding your entire network together. You have felt the pain of a bottleneck. It's a total traffic jam for your data. But what if you could take a bunch of regular roads and, like magic, just fuse them into a superhighway? Well, that's exactly what we're going to dive into today.
So, here's our game plan. We'll start by looking at that traffic jam. Then, we'll get into this weird paradox where adding more lanes actually makes things worse. From there, we'll reveal the solution, learn the two languages it speaks, see how to build it yourself, and then wrap it all up with the key things to remember. All right, let's get right into the heart of the problem. Just picture two of your main switches, the absolute arteries of your network, but they're connected by just one single cable. Every video call, every file you download, it's all trying to cram its way through that one tiny pipe. So is it any surprise that link is maxed out and your network feels, well, slow?
And this disk captures it perfectly. The before and after. On the left, that's your single-lane road. You can practically feel the frustration, right? The data packets are like cars stuck in gridlock, and that means lag and awful performance. But on the right, that's our goal. A massive, logical superhighway built from multiple physical links. We're not just adding lanes here, we're fundamentally changing how the traffic flows, which means we can slash latency and just multiply our capacity.
Okay, so the obvious fix seems simple, doesn't it? If one cable's not enough, just add another one. Double the cables, double the speed. Easy. But this is where networking gets a little bit weird. Because if you just plug in that second cable, your network's own safety features are going to kick in and shut it down, so you're left with a brand new cable that's doing absolutely nothing.
And here's the reason why. Meet the Spanning Tree Protocol, or STP. You can think of it as your network's hyper-cautious security guard. Its one and only job is to prevent these catastrophic loops that could crash your entire network. So when it sees two paths between switch A and B, it kind of panics. It goes, whoa, that's a potential loop, and it immediately blocks one of the links. I mean, it's doing its job, but the side effect is that half of your expensive hardware is just sitting there, totally unused.
Now look, I don't want to make STP out to be the bad guy here, because it's absolutely critical. Seriously, without it, a single bad cable could create what's called a broadcast storm, an endless loop of data that would take your network down instantly. So its logic is totally sound. Find all the paths and only let one be active. The problem is, it's just a little too literal. It sees two cables as two paths, and that's the problem we need to fix.
And this is where Etherchannel comes in and is just so clever. Instead of trying to fight against STP or, turn it off, it plays a trick on it. It uses a little bit of logical smoke and mirrors to make multiple physical cables look like one single connection. And that way, we get the best of both worlds. All the speed and all the safety.
So here's exactly how that trick works. We take our physical links, you can use up to 8 of them, and we logically group them into this one thing called a port channel. Now, when Spanning Tree takes a look, it doesn't see 8 different paths anymore. It just sees one big, reliable path. And since there's no loop, it just says, okay, that's fine, and leaves it alone. The result? Every single one of our links is now active, sharing the load and giving us all the bandwidth we paid for.
And the benefits are just huge. First, obviously, is bandwidth. 4 1 gig links don't just act like a 4 gig link. For all practical purposes, they are a 4 gig link. Second, the traffic gets automatically spread across all the active cables. But here's the best part: redundancy. If someone accidentally trips over a cable and unplugs one, the traffic instantly fails over to the others. The network doesn't even blink. And finally, it's just way easier to manage. You configure that logical port channel one time, and all the physical ports underneath just inherit the settings. It's clean, it's simple, and it's really powerful.
Okay, but you can't just throw any old cables together and expect this to work. The switches are, well, they're very picky. You have to think of the ports in the bundle as a team that has to be perfectly in sync. They all have to be the same type, no mixing a 100 meg port with a gigabit port. They all have to be running at the exact same speed and duplex. And most importantly, their VLAN configuration has to be a perfect mirror. Same node, same native VLAN, same allowed VLANs. If anything is mismatched, the channel just won't form. Simple as that.
Now, you could create these bundles manually, but it's way better to let the switches negotiate them dynamically. And to do that, they have to speak the same language. And there are 2 main protocols or languages that they can use.
The 2 you're going to run into are PAgP and LACP. So think of PAgP on the left as a sort of Cisco family secret. Cisco developed it, it's for Cisco gear, and it works great when you're connecting 2 Cisco switches.
But what happens when you need to connect a Cisco switch to, say, a Juniper or an Aruba? That's where LACP comes in. It's the open industry standard protocol that everybody else uses. It's basically the universal translator that makes sure all your different gear can play nice together.
And this really simplifies the decision, right? The rule of thumb is pretty simple. If you're running an all Cisco shop, sure, you can use PAgP. But for literally any other situation, especially a mixed vendor network, LACP is the industry standard and it's the way you want to go. Just think of it as your safe default choice.
So let's dive into PAgP. You've got 3 modes. On is just a manual override. It forces the link up, but it's risky because it skips all the safety checks. The interesting ones are desirable and auto. Think of desirable as the initiator. It's actively going out and saying, hey, anyone want to form a channel with me? Auto is more of a listener. It won't start the conversation, but it'll happily say yes if a desirable port asks.
And this matrix shows you exactly how that plays out. For the negotiation to work, someone has to make the first move. Desirable to desirable works because both sides are eager. Desirable to auto works because the initiator finds a willing listener. But auto to auto, well, that's like 2 shy people at a dance, both waiting for the other one to ask. Nothing ever happens because nobody starts the conversation.
Okay, let's switch gears to LACP. And here's the good news. If you understood PAgP, you already get LACP. The logic is identical, they just use different words. That risky on mode is the same. What PAgP calls desirable is called active in LACP. That's the one that starts things. And PAgP's auto is called passive in LACP, the one that just listens and responds.
And just like we saw before, this chart shows the only combos that work. You need at least one side to be active to kick things off. Active-active? Totally fine. Active-passive? Also fine. But passive-passive fails for the exact same reason auto-auto did. You've got 2 listeners and no talkers. It is the network equivalent of an awkward silence.
All right, enough theory. Let's get our hands dirty and actually see what this looks like on a switch's command line. You might be surprised by how straightforward the configuration really is.
It's really just a simple 3-step process. Step 1, you pick the physical ports you want to group together. Step 2, you use one command to bundle them into a channel group. This is the exact moment that magical port channel interface is created. And step 3 is the most important rule to remember. From this point on, you basically forget the physical ports even exist. All of your configuration, VLANs, trunking, the whole shebang, is done on that one logical port channel interface. That's what ensures all the physical ports stay perfectly in sync.
So here's a real-world example. First, we grab both interfaces at the same time with interface range. Then, here's the magic. Channel group 1, mode active. That command tells the switch, bundle these ports into port channel number 1 and use LACP's active mode to get it done. And once that's in, you see we jump right into the new interface port channel 1 to do the rest of our configuration.
Okay, once you've typed in the commands, you have to verify it's working. Trust, but verify. The show Etherchannel summary command is your single source of truth. Ignore everything else on this screen and look for these 2 letters, S and U. S just confirms it's a layer 2 switch port, but the all-important U means it's in use. It's up, it's working, it's passing traffic. If you see a D for down or anything else, you know you've got a mismatch somewhere, and it's time to go check your settings.
And when you troubleshooting, it is almost always one of these 4 simple things. Did you mismatch the VLANs? Is one side set up as a trunk while the other is an access port? Did you forget to make sure the allowed VLAN lists are identical on both ends? Or the easiest mistake of all, trying to make a PAgP port talk to an LACP port. I'm telling you, 99% of the time, your problem is on this slide. Match these settings perfectly and that link will pop right up. Okay, we've gone from a single-lane traffic jam all the way to a multi-lane superhighway. Let's just boil it all down to the 3 key things you absolutely have to walk away with. Here it is. First, remember your goal. You're trying to trick spanning tree so you can use all of your available bandwidth. Second, your protocol choice. Just use LACP. It's the industry standard. It's always going to work. Only use PAgP if you have a really specific reason in an all-Cisco environment. And third, the golden rule of maintenance. Once the port channel is made, only configure the logical interface. Never touch the physical ones again. Get these 3 things right, and you'll be an Etherchannel pro.
So we've pretty much mastered the art of bundling links for our switches at layer 2. And that leaves us with one final, kind of tantalizing thought. Can we take this same powerful idea of aggregation and redundancy and apply it one layer up the stack to our routers at layer 3? It's something to think about, and maybe a topic for another day. Thanks for joining me.